Thank you very much. Do you hear me?
Yes, we can hear you.
So everything that I'm going to talk about today is joint work with Nir Avni. So I want to start with a definition, which is the central definition for today's talk. So let gamma be a group and X a subset of gamma. We assume that it is not empty. The width of X in gamma is the minimal n. Now n can be either a natural number or infinity, such that every element in the subgroup generated by X is a product of at most n elements from X or their inverses. Okay, so and I want to talk. The first theorem that I want to tell you about is the following. So the yellow part is just the standard assumptions of the congruous subgroup property. So let K be a number ring, S a finite set of places of K containing all the Archimedean ones, O the ring of S integers of K, and G a connected, simply connected and absolutely simple group scheme over K, such that for every finite place V, GKV is isotropic. Now, I didn't put any restriction on the rank, because in this theorem, the rank could be 1. There is one more slide that I will deal with rank 1 groups, but basically in the rest of this talk, except this theorem and this slide, we will assume always that the S rank is greater or equal to 2, but not now. So the following conditions are equivalent. The first is that GO has the congruent subgroup property. The second is that every conjugacy class of the profinite completion of GO has a finite width. And the third is that there exists a uniform finite bound on the width of conjugacy classes of GO. Now, in this theorem, the fact that the first point implies the second and third point is relatively easy. This is just periodic analysis to show that the second point, and thus also the third point imply the first point. You need to use Rapinchuk's lemma. So it is not very hard claim, but it is based on a Rapinchuk's lemma. So the theorem implies that if there is a uniform finite bound on the widths of all conjugacy classes of GO, then GO has the congruent subgroup property, because then this property goes to the profinite completion, and you are done by this theorem. So the question is, can this condition really happen in arithmetic groups? So the first example is the following. So let D be greater or equal to 3 and O the ring of S integer. Then the claim is that there is a uniform finite bound on the width of conjugacy classes of SLDO. And I should have written that this is a result due to Carter, Keller, and Page. I forgot to write it. So let me go quickly over the proof. Bounded generation implies that there exists a constant C such that for every A in the ring O, there exists a finite index subgroup lambda A of SLDO such that every element of lambda A is a product of at most C elementary matrices of the form EIJ AB. So you put inside element from the ideal generated by A. So this is not strictly follows from the abstract definition of bounded generation, but this is really what you prove when you prove bounded generation in SLDO, that it's somehow uniform also with respect to ideals. Okay. Now, an easy exercise that there is a constant C prime such that for every non-central G in SLDO, there exists A in O for which the elementary matrix E1 to A is a product of at most C conjugates of G or G minus 1. So combining these 2 points together, we get that for every non-central G, there exists a finite index subgroup, lambda G's, whose elements are product of at most C times C prime conjugate of G minus 1. So we can cover a finite index subgroup by a bounded product, and now you use the fact that we know that we have the congruent subgroup property, so we know that in the profinite completion, every conjugacy, there is a uniform bound on the width of conjugacy class in the profinite completion, so we add this bound to C times C prime, and we get a bound. Okay, so this is SLDO. The second example is, let's stay in the assumptions of theorem 1. If the S rank of G is 1, then many conjugacy classes of GO have infinite widths. And this follows from a theorem of Westvina, Bromberg, and Fujiwara, who proved that the width of every word in every cylindrically hyperbolic group is either 1 or infinity. So in fact, I'm almost sure that if you go over their proof, you will get that every conjugacy class has infinite widths, not just many of them, but I just didn't go over it before this lecture, but it's probably true. Okay. So rank 1 groups are out of the question if you want to use theorem 1 in order to prove the congruent subgroup property. So the third example is, let G be as in theorem 1, but now assume that you have a place V such that GKV is compact. And because of our assumption that if V is finite, then GKV is not compact, this place must be a real place. So, and choose a bi-invariant metric on GR. I will always assume that the diameter is 1. It's just some normalization of the bi-invariant metric. It doesn't matter. Now, since GO is a dense subgroup of the compact group GR, for every G in GO, the width of the conjugacy class of G, when we think about G as an element of GR, is at most the width of the conjugacy of class of G when we think of G as an element of GO. This is an easy exercise. Now, if I take an element G in R, an edge which is either conjugate to G or to its inverse, then the distance of edge from the identity is exactly the same to the distance of G from the identity. So if now edge is a multiply of K such elements, I have an upper bound of its distance from the identity. It's at most K times the distance of G from the identity. On the other hand, GO is dense in GR, so we can choose a sequence Gn of non-central elements, GO, which converge to 1. So it's non-central elements. The group is simple modulo its center, so the conjugacy class generates everything. But now the conjugacy class is all the elements inside it are very close to the identity, so it will take them a lot of time to cover everything, right? I will have to take a lot of multiplication in order to cover everything. So oh, sorry, what did I do? So we get that the limit of the width of this conjugacy gas goes to infinity. So I don't know what is going on. So, oh, sorry, I choose. I just a second. Okay. Okay, I hope that now to be okay. So if we have a compact places, we cannot opt to have a uniform bounds. We have to take the compact places into consideration. So the main conjecture which I want to talk about in this lecture is the following. So let G be as in theorem 1 such that the S rank of G is at least 2. And let S com be the set of all compact places. Then there exists a constant C such that for every G in GO, the width of the conjugacy or class of G inside GO is at most C times the maximum of the width of G of the conjugacy class of G in GKV when V runs all over the compact places. So this is the best we can hope for. And it turns out that this conjecture, if true, is good enough to prove the congruent subgroup property. So let's prove that it's good enough. It's not hard. A sufficient condition for a constant D to be a uniform finite bound on the width of conjugacy classes in the for finite completion is that every coset of every finite index subgroup of GO contains an element G such that the width of G in GO is at most D. So this is a sufficient condition. And now focusing for a moment on the local behavior, then there exists a constant D such that for every compact V and every G in GKV, if you look at the width of the conjugacy class of G, it's bounded from above by D divided by the distance from the center of GKV. And in fact, it's proportional. You can bound it also from below. It's basically one over the, not one, some constants over the distance. Okay. Now, every coset of every finite index subgroup of GO is dense in the product of GKV all over the compact places. And dense contain an element G such that for every compact V, the distance of G from the center is at least 1 over 4. And I remind you, I normalize the metric so the diameter is 1. So by the previous point and the conjecture, we assume that the conjecture holds, we get a uniform bound on the width of the conjugacy class of G, which is 4CD. And then once we get a uniform bound, we know that there is a uniform bound in the profinite completion, so we know that that you have the congruent subgroup property. Okay, so before trying to prove this conjecture, or at least in some cases to prove it, let's try to understand what is going on. So we saw that in SLDO, bounded generation implies the existence of a uniform finite bound on the width of conjugacy classes. The converse is also true by the following theorem. So this is a theorem of Suslin. So let D be greater or equal to 3, then there exists a constant C such that for every commutative ring R, every element in the conjugacy class of the elementary matrix E1D with 1 in the ID entry is a product of at most C elementary matrices. So this is true in any ring. This has nothing to do with arithmetic. So now we get that if this conjugacy class has a bounded width, then you have bounded generation by elementary matrices, which is the converse of that we wanted. So bounded generation and the main conjecture are closely related in the isotropic case. You probably, it's not a theorem, but you probably in many cases deduce one from the other. So what happens in the anisotropic case? So we know that bounded generation cannot hold in the anisotropic case because the theorem of Korvaja, Rapinchuk, Ren, and Zanier. But why it cannot hold? What is the main reason that they found? And it is the following. So if you take a unipotent matrix, then the entries of the nth power of A are polynomials in N. On the other hand, if you take a semi-simple matrix, then the entries of the nth power of A are exponential in N. And it's much harder to solve exponential equations with integers than it is hard to solve polynomial equations. But what happens if you talk about conjugacy widths? So if you conjugate A by B, and you're thinking about the entries of A as constant, but on the entries of B as variables, you get that the entries are polynomial in the entries of B. So you return to polynomial equations. And this leads to the hope that still there might be a chance that if you talk about a conjugacy width, also in the anisotropic case, you can have finite conjugacy width. So in some sense, the way to think about it is that you have a property that in the isotropic case is very similar to bounded generation, but differ from it in the anisotropic case, and that's why you have a chance that it will hold in the isotropic case. Sorry, I have to drink a second. Okay, so here the second theorem is the following. So let n be greater or equal to 10 if the standard positive defined quadratic form of dimension 2n, O is the localization by 2 of the of C, G is spin of F, and gamma is G of O. Then, for every n, the set of n's powers has a finite width in gamma. So it's not conjugacy classes, but it's still a result about widths. But if you assume the general Riemann hypothesis, then the conjecture holds for gamma. So in this case, it means that there exists a constant C such that for every G in gamma, the width of the conjugacy class of G is a small c times the width of the conjugacy class of G, but when you think about it as an element of GR, of spin over R. Now, before continuing, I just want to say two things about this theorem. We do not think that there is something special about this specific form. We think that it's true for every a form which is as an high enough dimension, and we are working on it, but we didn't finish to prove it for a general form yet, but we do think it's true. And the second thing is the use of GRH. So it's not really you use a very weak consequence of GRH, something that is related a relatively weak version of Artin primitive root conjecture. And at least I've been told by number theorists, I'm not a number theorist, but that what we need can probably be proved without general Riemann hypothesis, without any assumptions, but it's not something that we will try to do because it required number theoretic techniques that we are not expert in. Okay. So what I want to try to show you in the rest of this talk is that this conjecture is really very related to the congruous subgroup problem. Not only that it implies the congruous subgroup problem, but you can think of it as a congruous subgroup problem, but not for the group gamma itself, but for a ultra power of gamma. And in this way that most of the steps that you need in order to prove this theorem are very similar to the steps that you take in order to prove the congruous subgroup property in this group. Okay. So sketch of proof. And it will be a long proof. This is the reminder of the talk, but I will try at each point to summarize where we're at, that it will be that even if you don't understand some part, you'll be able to follow the following parts. So let K, O, G, and gamma be as in theorem 2, and fix some non-central element. So Knesser was the first one to prove the centrality of the congruous kernel in such situation. And if you look at this argument and you do them really carefully by following really the computations, you get the following. That there exists a constant C which depends only on the distance of G from the center. Oh, sorry, this is written the center of G from GO. It should be the center G of R when you think about it as an element of the real points. And the non-zero ideal J, which again depends on G, is such that if you take a X and Y in the J congruent subgroup and you take their commutator, then this commutator is equal to the product of at most C conjugate of G of the inverse or of the inverse of G. So this is the first thing. And the second thing is that there is a constant C prime and a non-zero ideal J prime, such that for every non-zero ideal I, there exists a non-zero ideal I prime, such that if you take an element X in gamma I prime and an element Y in gamma J prime, and you take their commutator, then you can, this commutator is equal to the product of at most C primes commutators, but now the entries of the commutators are taken from gamma I. So and the point is that J prime is fixed. It does not depend on I or on anything. And also C prime is fixed. So just to make life a little bit easier, in this talk, we assume that J is equal to J prime is equal to O. And we know that gamma is perfect. So item 2I implies that it's enough to show that the set of commutators of gamma has a finite width. Why? Because we know that by bounded product, I can get from the conjugacy class to every commutator. Now, if from every commutator I can get by bounded, if from the set of all commutators I can get by bounded multiplication to every element, I'm done. And recall, because here we assume that J is equal to O to make life a little bit simpler. So now we translated the question from conjugacy widths to commutator widths. Okay, and now we need some model theory, but very, very, very standard model theory, nothing fancy. There is no magic inside. There is no deep theorem. Everything is elementary in the model with respect to model theory in this talk. So let U be a non-principal ultrafilter on N, and you take gamma star to be the ultra power of gamma with respect to this ultrafilter. So what does it mean? You take the direct product of gamma countably many times with itself, so you can look at the elemental sequences, and you divide by sequences which are almost always the identity, and almost always means that the set belongs to this ultrafilter. So by Vosch theorem, the group gamma star, which is simply G of O star, you can take the ultra power of O or of any other object, satisfies the same first order sentences as gamma. So this is an important theorem, but the proof is very technical. The proof goes the way that you think it's proof. There is no really hard part in it. And in any case, in all the places where I'm going to use Vosch theorem in this talk, it's even simpler. I'm using very simple first order sentences that it's easy to prove by hand that they are old in the ultra power. Okay. Now, a standard argument implies that the width of the commutator, the set of commutators, is finite if and only if gamma star is perfect. So this is really standard, but I want to sketch the argument. So since gamma is perfect, if the width of the set of commutators is finite, then there exists a constant C such that every element of gamma is a product of at most C commutators. But this is a first order sentence, you can write it. So by Vosch theorem, every element of gamma star is a product of at most C commutators, which means that it is perfect. On the other hand, if for every n there exists Gn, such that Gn is not a product of at most n commutator, then look at the element whose n's coordinate is Gn or its equivalence class, because we take quotient. Then if you think about it, for you see that it cannot be an element of the commutator subgroup, so you have an element which is not in the commutator subgroup, so the group is not perfect. So now we translated the problem to show that the ultra power is perfect. Okay, sorry. Now, the ring O is not a ternarion. However, every finally generated ideal of O star is generated by two elements and is a ultra product of standard ideals. And the reason that for this is you can write a first order sentence that if I'm generated by three elements, that I'm actually generated by two elements. And then another set that I say if I generated by four elements, I actually generated by two elements. So this way, and this sentence is first order, so it's also working O star, and you get this. So now we want to define two families of subgroup of GO star. And I remind you, gamma star is equal to GO star. So I can talk about congruent subgroup in gamma star as usual, as I read in the standard definition. But we also want to talk about what we call the I-congruent subgroup, which is to take the I-congruent subgroup and to intersect it with the commutator subgroup of the full group. so these two families of group induces two group topologies. And one is finer than the other. It's clear that the congruence topology is finer than the congruence topology because every open set in the congruence topology is also, every basic neighborhood of the identity in the congruence topology is also open in the congruence topology. And notice that it is enough to look just at finitely generated ideals because any ideal contains a finitely generated ideal. So we really can speak just about the ideals that we understand, not about the strange ideals that exist in this ring. Now we get a commutative diagram. So this is the diagram that we get, and I want to tell you what is clear in this diagram and what is not clear in this diagram. The fact that we have errors and that they commute, it's clear. There's nothing surprising in this. The only non-trivial thing is that the horizontal errors are isomorphism. The fact that the horizontal errors are injective are clear from the definition of the congruent subgroup is simply the intersection of the commutator subgroup of gamma star with the I congruent subgroup. So it must be injective. The question is, why is it surjective? Why the horizontal errors are surjective? And the reason that they are surjective, because if let's return to the standard model, gamma modulo gamma I, the ith congruent subgroup, is perfect, but not only it's perfect, every element is a product of a bounded number of commutators in this finite quotient. And this finite number does not depend on the ideal I. So I can write a first order sentence and say that for every ideal which is generated by two elements, gamma modulo gamma I, every element is a product of C commutators. This is a first order sentence, so it's also in gamma star. So this means that gamma star modulo gamma star I is perfect for every two generated ideals I, and from this you get that it's surjective. And you can take completion with respect to these two topologies, and you get the congruence completion, whatever it is, and you get the congruence completion. And the nice thing is that you can actually compute here the congruence completion because of what we said in the previous step. It turns out that the congruence completion is simply the direct product of the abilization of gamma star with the congruence completion. And okay. So just a few remarks at this point. The identity map of GO as extension to a continuous map row from the congruence completion to the congruence completion. This is by the universal property of completion. But this is quite confusing if you are used to think about the standard case. There is no reason to expect this homomorphism to be surjective. You get it for free in the standard case because you're talking about compact spaces. Here it's not compact. It's inverse limits of discrete spaces. You don't get it from free. But luckily, we were able to compute the congruence completion, so we know that exactly what is rho. It's just projection to the right coordinate. And this is just I just wanted to make it clear that inverse limit of discrete spaces which are not finite is really terrible. The inverse limit can be empty even if all the maps are surjective. So we do not understand the exact structure of the congruence completion, but we are lucky because there is an embedding of the ultra power of the for finite completion of the standard model in the of the congruence completion of the standard model in the congruence completion of the non-standard model. And all the computation that we are going to do will be inside this embedding. So we will deal with the creature that we understand. And the third thing is just something that looks strange at this point is that we get that the congruous kernel is central for free, where in the standard case it's the hard part. It's considered to be the hard part of the proof. Okay, so the congruence topology as an extension to a topology on GQ star, this is trivial. But now you want to say that also the congruence topology and as an extension to a topology on GQ star, and this is not trivial, and this is not trivial because of in some way we defined the congruence completion in an unnatural way, and we define it in the unnatural way in order to get over the problem with inverse limit of infinite discrete spaces. But now we pay the price that we do not know that it's not clear, at least that you can extend it to a topology on GQ star, and it turns out that the argument that you need to show that you can extend it to a topology on GQ star are exactly the same argument that in the standard case you need in order to prove the centrality of the congruous kernel. So we didn't get anything for free, we just change the place of the difficulty. Okay, but the end point is that you can extend this topology to a topology on GQ star. So since the homomorphism at the level of the integral points is projective, also at the level of the rational points, this rho is surjective, and we get a central topological extension, which has the following properties. The kernel is a discrete subgroup. Rho is a continuous section over an open subgroup. And rho is a section over GQ star, and the section has a dense image in the congruous completion. Okay, so this is what we have. So now we go back to Knesser again, but for a much earlier work of Knesser, that Knesser proved that every element of GQ is a product of a bounded number of commutators. So the same is true for the ultra power of GQ, which is just G of the ultra power of Q. In particular, GQ star is perfect. And now, because you have this central extension and you know that GQ star is perfect, you get that, and you have a splitting with a dense image, you get that the abelization is trivial if and only if the central topological extension, the following central topological extension has a continuous splitting. So now a definition, a discrete GQ star metaplectic extension is a central topological extension such that the kernel is discrete. There is a continuous section over an open subgroup, and there is a section over GQ star. And now we translated the original question to the following question. It's enough to show that every discrete GQ star metaplectic extension has a continuous splitting. So we started with finite conjugacy widths, and now we want to show that some cohomology vanish. Okay. but as usual, it's hard to deal directly with the anisotropic case. So we look at the split case. Everything that we said so far, we could have done for the standard split form and for the standard split group. So the definition of what is a discrete HQ star metaplectic extension should be clear when H is the standard spin group. And what we show that every edge Q star metaplectic extension has a continuous splitting. So let's assume for simplicity that the extension has a continuous split in psi2 over the congruous completion of the integral points. And let's psi1 be a splitting over the rational points. And what we want to show that in fact psi1 is continuous, so we can get a splitting of the full sequence. So as usual, because this is a central extension, psi1 and psi2 agree on the commutator subgroup of the intersection of the rational points and the congruous completion of the integral points, but this intersection is simply the integral points. So psi1 and psi2 agrees on H O star on the commutator subgroup of H O star. Okay. But now I'm going to use bounded generation, but for the split form. By bounded generation, every element of GO is a product of a bounded number of commutators. So the same is true for H O star, again, because this is a first order property. Thus, as O star is perfect, so we get that psi1 and psi2 agree on H O star, so psi1 is continuous, so you have a continuous splitting. So we know that every HQ star metaplectic extension splits. Okay, so now let's return to the problem of a GQ star metaplectic extension. Since O is the localization at 2 of Z, if we look at a form F and F prime, they are equivalent over the congruous completion of O. And that's also over the ultra power of the profinite completion, because O embeds in it by the diagonal embeddings. But now we said before that we have an embedding of the ultra power of the profinite of the congruous completion of O inside the congruous completion of O star. So we get that there is a topological isomorphism alpha from GQ star to from the congruous completion of GQ star to the congruous completion of HQ star, such that it preserves the integral points. So now what we get a central topological extension, but of the split group, and this extension has a continuous splitting over an open subgroup and a splitting over the copy of GQ star inside the congruous completion, which is, we do not understand exactly how it sits, but we understand that it sits there. So by the previous step, it is enough to show that there exists a splitting over HQ star, because then this is an HQ star metaplectic extension, and we know that HQ star metaplectic extension splits. Okay, so this slide is just I remind what is a Steinberg symbol. There is just a reminder. So there are maps H1 and H2 from the group of invertible elements in Q star to the spin group, and a map called the Steinberg symbol from Q stars, the invertible Q stars times the invertible Q stars to the kernel of this central extension, such that for every AB in Q stars, H1A and H2B commutes, and AB is just the commutators of some lift of H1A and H2B to E. So it doesn't matter any lift because it's a central extension, and because these elements commute, their commutators, the commutator of the lift fell inside D. And this map is called a Steinberg symbol, and the theorem is that over a field, the extension of the split form split even though only if the Steinberg symbol is trivial. And Q star is a field, because the axioms are field are of first order. So you take a field, you take its ultra power, you get a field. Okay, so I just repeat what we now have to do. So it is enough to approximate, and I will tell in a minute something about what is I'm not going to explain exactly, but I will give an example what is approximate. Every pair of the form H1A and H2B by a product of commuting pairs from alpha GQ star. An approximation means that the commutator, that we will know that the commutator of the original pair will be equal to the product of the commutators of the commuting pairs from alpha GQ star. Why? Because we have a splitting of alpha Q star. So if I'm taking a commuting pair there and I lift it and I take its commutator, it will be trivial. So the approximation consists of two steps. So let's see denote be the subgroup of D, which is generated by the values that the Steinberg symbol gets. So the first step is to show that C is divisible. And this can be done in a similar way to the work of Prasad and Rapinchuk on the computation of the metaplectic kernel. They do this approximation, and in the standard case, to prove that the congruent kernel is divisible, it is enough because a divisible profinite group is trivial. But here the kernel is discrete. It does not have any topology. A priori, it might be the additive group of the rational numbers with respect to addition, a discrete group. You have no reason to expect it to be so it might, so it's not enough. So the second step is to show that C has a finite exponent, and having a finite exponent and divisible is equal to being trivial. And this is the place where we use the general Riemann hypothesis, because here the proof relies on a version of our thin conjectures on primitive roots. Okay, so I think that I'm done. Thank you.
Okay, some questions, comments? Yes.